Good, af- good afternoon, participants. We'll start the session. For this second session of day one, we have Dr. C.N. Shyam Kumar as the resource person. He is assistant professor in NIT Calicut, and his academic background is in material science. He has completed his MS from IIT Madras in 2014 and PhD from Technical University of Darmstadt in Germany in 2019. So, without much formal introduction, I welcome Dr. C.N. Shyam Kumar to the session. Welcome, sir.
Thank you, Kumar. Thank you for the introduction, and also thank you for the opportunity to discuss some of the things regarding carbon to you all. Um, Basically, I'll be talking about um, engineered carbon materials, that is basically from biomass resources and all. And I would like to tell that you can stop me at any time if you have any questions or anything. You don't have to wait until the last slide and all. So now I think I'll hope I'm audible and everything is fine, right?
Yes, sir. It's audible.
Mm, So are you able to see my slides?
Yes, sir. Visible.
Okay. So then I think I'll switch off my video. Okay.
Okay.
So the slides are visible, right?
Yes, sir. Slides are visible.
And it is in the presentation mode, right?
Yeah. It's presentation.
Okay. Yeah. Okay. So once again, thank you for this opportunity. So as I don't, you can stop me anytime. Uh, in a way, it's a bit boring uh, to talk like this without you all in front, but still. So I'll be trying to give you some overview about how we can engineer or tune carbon materials for different applications, and with some of the examples that we are doing here. And carbon, as you know, we all very well know carbon. It is a very interesting element, and you have different hybridizations, and the whole thing actually is with its electronic configuration, which is 1s2, 2s2, and 2p2. And with the changes in the hybridization, you can have sp3 carbon. It can form the hardest material in the world, as well as the softest one, which is the graphite. And it is all depends on the hybridization, how it is faring. Uh, this this property of actually having different hybridization can be of help for us in different ways. Actually, since the properties depend on the microstructure, we have the possibility to tune this the microstructure, thereby tuning the properties. And you know about the different carbon nanomaterials that is being discussed maybe over last maybe 30, 40 years, right from the carbon nanotube, which was started discussion around 1990s. Then fullerenes, then came the wonder material, which is the graphene, um, which is in I think 2008. Oh yeah, I think 2008 or so. I don't exactly remember uh, the year, but these two gentlemen were able to exfoliate graphite into a single layer, and this is actually from the Nobel Prize site, where it is actually strong and it can hold a cat uh, with with a hammock which is even lighter than the cat's whisker. So it has all the properties. So we know about these things. We have heard about carbon nanotubes, we have heard about graphene, and then you have the quantum dots. Then comes the different, um, different allotropes and different forms of carbon. Just one more thing regarding this graphene before I go to the main topic here. And one thing that maybe you all know that this the whole thing. I would say this is one of the very simple experiment uh, that might have resulted into a Nobel Prize. They just used a Scotch tape, which is our normal cello tape that we see, and a piece of graphite. And the idea was that, because you have the van der Waals force between the two layers, so what if we keep on exfoliating, and then finally you should end up in in a single layer of graphene. Even though there are now different ways to produce single layer graphene, which is CVD. You take a copper substrate and then do some chemical vapor deposition to make a single layer graphene. Still, for experimental purposes, people use a Scotch tape and a graphite, thick graphite flake, I would say, to make graphene and do electronic measurements on that. In fact, I had a friend who used to say that, okay, my consumables are over. I need to go to a stationery shop to buy a Scotch tape, and she keeps on exfoliating, and then finally transfer it to the silicon dioxide, and then then they make contacts and then do electrical measurements. I really like this experiment. One of the very simple, inexpensive, not uncomplicated um, process which resulted into a wonder material. And to let you know, actually, graphene was theoretically, the theoreticians told that theoretically graphene is not possible. It uh, won't be stable. But but finally they could exfoliate a single layer of one atomic layer of carbon, sp2, and that started the whole discussion on graphene. Now you can see a number of publications and other things. So we know about all those things. We know about diamond, we know about graphite, carbon nanotubes, fullerenes, and there is one class of material which is not entirely different, but we call them pyrolyzed carbon. So this is what we will be discussing for the maybe next 45 to 50 minutes. So pyrolyzed carbon is now into different technological applications. It's widely used in variety of applications like electrode materials in batteries and supercapacitors. If you know, the lithium-ion battery uses graphite. But when it comes to the post-lithium-ion batteries like sodium or potassium, the graphitic layers cannot host the bigger potassium and sodium ions. So there you need a material which is not ideally having the exact graphitic layer thickness, which is 3.34 angstrom. So you need to have a bit of disorder nature there, so that the layers are not perfectly graphitic, and you have more space between the layers, so that the bigger atoms can go. So this is where actually the uh, hard carbon, they call it. It is also a pyrolyzed carbon. So hard carbon electrodes are used in battery applications, supercapacitors, and other things. And catalyst support for chemical reactions. These are highly porous. So you have more active sites for chemical reaction, water and air purification, and also even they used as reinforcements in composites, both polymer composite as well as metallic composites. This is actually biocompatible, so you can use it as implants and coatings and implants, and sensors, biosensors, drug delivery, and also thermal and corrosion resistant coatings. So there are a wide variety of technological applications where you can use this pyrolyzed carbon. And one of the advantages that why it is so popular is that you have, as I told, you have the possibility to tune the microstructure. you have the possibility to tune the morphology, and thus you have a control over the properties. So basically, you can think of a property-specific material tuned for a specific applications. So what is this pyrolysis, So, and what is the difference between normal burning? So because if you burn something, you also make carbon, right? But what is the difference here? So pyrolysis is basically heating without oxygen. So you heat it in an inert atmosphere, or you heat it in vacuum. But when you do normally burn it, so you make carbon, which are mostly amorphous, sp3 hybridized, and the graphitic content, that is sp2 content, is very low. And some of the properties such as electrical conductivity, thermal conductivity, and other things are because of the sp2 nature. So you will lose all those things. And the yield is very low because you lose everything, because oxygen, carbon and oxygen are very good friends. So they make CO2, CO, and also and other volatiles will go if there is oxygen. So your yield is very low. But in the case of pyrolysis in inert atmosphere or in a vacuum, high vacuum, the carbon won't uh, go as carbon dioxide or carbon monoxide because there is no oxygen. And if you have a precursor material with aromatic structure, these structure can freeze and form as the building block for sp2 carbon. Because if you remember this aromatic ring, if you remove all the other volatiles and other things, then the carbon ring will freeze, and these carbon rings are the building blocks for the sp2 carbon. So basically, you have more sp2 content. Because of that, you have enhanced conductivity. And since it is sp2, you will have layered structure. It is not completely like graphite. We will discuss. And the yield is high because the carbon is not going. Carbon as such will stay, and the other volatiles will go. That's true, but carbon will be there, and more controllable. So you have the possibility to control uh, the microstructure and morphology. So basically, yeah, this is how what it happens. It is a thermochemical decomposition, and after the initial uh, removal of volatiles, we will see that in the coming a carbonaceous backbone will be forming, and this carbonaceous backbone means there will be some aromatic rings or sp2 rings, I would say, which is from the aromatic molecules. And there will be also this disordered carbon, the other carbon which is there. So it is a mixture of initial stages. It is a mixture of sp3, sp2 carbon with a low sp2 content, I would say. And as the temperature increases, sp2 is a more stable form of carbon. So there will be a conversion from sp3 to sp2 carbon, and there will be an extension of the sp2 network. And finally, basically, that's what it. These carbons are basically called non-graphitizing carbons, in the sense like it won't finally form a layered graphite even if you go to very high temperature because of the initial uh, misorientations. It won't. The layers won't completely be flat and form graphite. There are some precursors which, if you heat to very high temperature, finally end up in graphite. But in this case, it won't end up in graphite, but it will be graphitic. So there is a slight difference in this too, because graphitic means it will be completely sp2. There won't be any sp3 carbon left, but it won't form a graphite. So that is why it is called non-graphitizing carbons. And now coming to, as I told, you can pyrolyze any kind of material. So you can do polymer. You can take polymers and with aromatic molecules, and then you can pyrolyze it to form pyrolyzed carbon. Uh, there are there are groups working on engineering the polymer itself to have more graphitic content, self-assembled monomers and all, so that you have more aromatic rings, and finally you will get you can tune the graphitic content. But here, actually, what we started is to look into the biomass, because biomass inherently is lignocellulose, so it contains lignin, cellulose, and hemicellulose. If you take any biomass, this is the basic three constituents, and the amount of this varies. In some cases, it will be more lignin. In some cases, it will be more cellulose and hemicellulose. And when it comes to lignin, lignin is the aromatic structure. So the amount of lignin decides your amount of sp2 content. And as I told, you can take different kinds of biomass, and there are a lot of work happening in making it in different shapes, spheres, dots, fibers, sheets, hierarchical carbon, all those things, and it is being used for a lot of different applications. So basically, when you look at it, um, you have the possibility, we can think of it too with, I would say, four things you can engineer in this. One is, as I told, the graphite content, how much sp2 or the fraction of sp2 and sp3, which again decides the final properties. Second thing, obviously the porosity, because when the volatiles and other things are removing, this carbon is inherently porous. And you can again engineer the porosity by changing the graphitic temperature and then the graphitization conditions or the pyrolysis conditions. You can actually engineer the functional groups. What are all the functional groups you need in this carbon, whether you want to remove everything or you want to keep part of it, because these functional groups will add some specific properties to this carbon. And obviously the morphology. That largely depends on the starting material. If I take coconut coir, you get a fiber type of thing, or if you take coconut shell, you get hard carbon, or you can powder it, all those. But there also a possibility to have a control over morphology by carefully selecting the starting material. So we will be briefly looking into how these four things can be engineered to have different properties, and we will be discussing some of the applications. So the uh, whole point of this introduction is just that we have a possibility to have a property specific functional carbon material. Now we go to some examples which we all know very well is the coconut coir. This coconut coir is one of the lignocellulose biomass which contains very high lignin content. So if you can take that and pyrolyze it. So this is an example where we took a coconut coir. These are coir, not the fiber, because this is after the retting process and all. So this is what we use for making coir, and so it is they use some treatment to make it bit hard and strong. So we took that and did a pyrolysis, just heated it until 1000 degrees Celsius in an inert atmosphere, argon or nitrogen. So what you can see is that one thing, as the temperature increases, you can see first thing is that the morphology remains same, because you still get carbon fibers, I would say, and you can actually mix it with the like you can actually connect those things. So the morphology remains same. And these are Raman spectroscopy, which we use to uh, measure the graphitic content. And what we observe from this is that, please don't worry about that. But what this shows is that as you increase the temperature, the graphitic content is increasing from 600 to 1000. And you can see when you look at the SEM images, you can see the porosity is also evolving. So at 1000, you have a moderately graphitic porous carbon. Something similar also you can observe with the coconut shell. I'm just giving you some examples. Coconut shell. Here also you can clearly see from Raman, actually you can see that you have a increase in the sp2 content as you increase the temperature from 600 to 1000. You can use the D and G band to have an idea about the increase in the graphitic content. And from the SEM images, you can see uh, there is a porosity. The porosity is increasing. So now again, you have again here you have in a way three different microstructure in both samples at 600, 800, and 1000, and the properties will change because of this morphology. No, the microstructure and morphology. Now the question is that when you look at it, as I told, still at 1000 degrees Celsius, you have, I would say, more moderately graphitic carbon. It is not yet completely graphitic. So what we should do? One possibility is that you can increase the temperature. So what we want is that we still want some more possibility to tune the sp2 content so that we can again have a more window of changing the properties. So how to do that? One way is that if you increase the temperature more, definitely, as I told, uh, more stable one is sp2 carbon. So this sp3 will now transform from uh, sp3 to sp2, and maybe more than 2000 or 2500. This carbons are very stable at inert atmosphere at very high temperature. You can even heat to maybe 300, 3000 degrees Celsius, and still they will be stable. And you can actually heat to very high temperature. This is one way to increase the sp2 content, but you are limited by the experimental constraints. Can you hear me?
Yes, yes.
It's okay, right?
Yeah, I think our net was disconnected.
Yeah, here also I think it's raining heavily, so maybe here also. But
Okay.
let me know if I'm kind of you miss me
Sure.
in between. Yeah, yeah. So now the question is that how to increase the graphitic content. One way, as I told, is to increase the temperature, but that won't help all the time because you don't have very good uh, furnaces that can go until that temperature. So another way is that you can use a catalyst. So this is what we are trying to do with catalytic graphitization. So another way that you facilitate the conversion from sp3 to sp2 through a catalyst. That way you can increase the sp2 content so that you don't have to go to a very high temperature. Within our furnace itself, we can do this. So this is one thing that we try to increase the graphitization by using a single step nickel nitrate solution. So you dip your coir or even shell in a nickel nitrate solution and allow the nickel nitrate or the material to soak in maybe for 8 hours or something, continuously stirring. And then you take it out and do a pyrolysis like the previous time. So what happens in that time is that now it is not the biomass alone, but you have nickel as a catalyst. In fact, I think it maybe like what we think is that initially after the initial carbonization, carbon is a reducing agent. Carbon is reducing nickel nitrate to nickel, and then this nickel is acting as a catalyst to improve the graphitization. Again, from the Raman, we could understand that the graphitic content has considerably increased now because you have the 2D peak. So now what we have is we have almost completely graphitic carbon, which is very highly conducting, more mechanically stable. And also on the top of that, we have a very fine nickel particle, which is dispersed all over the carbon. So basically you have a nickel carbon composite with a one-step synthesis. And this is again one more characterization technique that we use XRD. Yeah, XRD is used to understand the improvement in the graphite content also. Now, till now what we have done is that we were trying to increase, or with a normal single pyrolysis, we are trying to increase the graphite content until 1000 degrees Celsius. But that is not sufficient all the time. So what we do is that we use a catalytic method to increase the graphitization. And with Raman and XRD, we could understand now that it is highly graphitic. Now, when it comes to engineer a carbon material, to tune the properties, you need to have a very good understanding of the microstructural evolution, how the microstructure is changing, how the internal structure is changing. And most of the characterization that we do is actually something like XE2, post-mortem characterization. So you take your sample, you heat it to 1000, take out your sample, and look at it in Raman or in SEM or in a TEM. Okay. But what happens in that case is that since the pyrolysis is a very dynamic process, there are a lot of changes that is happening during the process. So you lose the track of all those things. So sometimes to have a proper understanding of the microstructure or microstructural evolution, we need to have a bit more advanced characterization or bit more careful look into the process. So that is what I'll be just briefly telling you in the next couple of slides to how we try to have a more understanding of the structural evolution. Now I'll just tell you, just wait, because I'm telling all these things to show you some of the properties and functions, and then we will be able to correlate back all these things that we have seen here. So one thing is actually you can do a in situ Raman. You take the Raman spectroscopy, because all those other Raman spectroscopy that you've seen is after the heating, you take out the sample, okay, and then you do Raman. But what if we can take the Raman spectra while you are heating? In that case, you will be able to understand by correlating with some other characterization techniques. So this is something called a TGA. It measures the weight loss of your sample, this graph down. It measures the weight loss of your sample while heating. So you can have an understanding at what point or what temperature the volatiles are starting to move or separate out from the sample. And you can actually correlate it with the Raman. So just to tell you this, why we did this was that we can now understand at what temperature the initial carbonaceous backbone is forming. At what temperature the carbon, the biomass is now converting into carbon, where the mixture of sp3, sp2 carbon when it is happening. So we can understand this with this Raman, and actually from this we can say that it is somewhere in 350 degrees Celsius. And from the TGA, we can see that the maximum weight loss is happening around 300 to between 300 to 400 degrees Celsius. So it is when the volatiles are removing and it is becoming carbon. So this is with coconut coir, and similar things can also be, because the graphitization trajectory will be similar. So there might be some shift in the temperature, but similar trend you can also expect on the other lignocellulose material also. You can also look at the shrinkage, how, because when the volatiles are removing, there will be a change in the size of the sample. So you can see it is the maximum change is happening from somewhere around, I would say between 300 to 100 degrees Celsius, which is coming down from 120 micrometer to 100 micrometer. So you can correlate this. All these insights will help you to tune it better. Now, with Raman, we can understand how when it is becoming carbon and how the graphitic content is increasing, but you also need some uh, more careful look or high resolution uh, imaging techniques to look into the evolution of the microstructure. So this is TM, and actually you can see from 600 to 1000, you can see the evolution from a disordered carbon to a small graphitic flakes, which is happening at 1000 degrees Celsius. So now you know that there is a higher amount of sp2 at 1000 degrees Celsius, and the sample is almost kind of a flaky uh, graphitic structure. So this is okay. Just again, just this is with the normal samples. And if you remember, we talked about adding nickel, right? So nickel is improving the graphitic content. So, but how it is improving? What is the final microstructure that we are getting? For that, we can do some TM, and actually we can heat inside the TM, which is called in situ TM. So you can see that these black particles are nickel particles, which are coming together, and also in the way that it is actually graphitizing while it is moving. So this part is kind of amorphous carbon, and I would say this part is graphitic. So this layers are graphitic carbon, and also here you can see the black part is receding, and the highly graphitic layered structure is being formed here. So now we know that the nickel is moving and coalescing, and in that path, actually it is being graphitized. One thing that we need to keep here is when you look at the nickel particles are not exposed to the atmosphere, but it is being covered with graphitic carbon. So what you have is small nickel particles, which is covered by few layers of graphitic carbon. So you have a core shell structure. So this is with the microstructure. I'm just not kind of making you bored with these images and other things. So basically, till now, what I wanted to convey is that you have the possibility to again tune the microstructure by varying the pyrolysis condition as well as the starting material. To have a proper tuning of the microstructure, you need to have a proper understanding of the microstructure, which in that case, if you have some kind of this advanced techniques like in situ Raman or in situ TEM, you will have better understanding of the microstructural evolution. So we know that the initial carbon conversion to carbon is happening around 350 to 400 degrees Celsius. And by that time, almost all the main volatiles are leaving the biomass. So the carbonization starts there. And you can continue like that until 1000 degrees Celsius without any catalyst, but you won't get highly graphitic carbon. But if you want to improve the graphitic content, you need to use a catalyst. And when you use a catalyst, what happens is that the nickel is actually is it the graphitic carbon is basically precipitating out from the nickel. It is called dissolution precipitation mechanism. So now we have uh, at normal condition at 1000 degrees Celsius, you have a moderately graphitic carbon, which means that a mixture of sp2 sp3. And when you use uh, nickel at that temperature, you will have highly graphitic carbon. Now, with this understanding of this microstructural evolution, now we look at three examples of using this biomass-derived carbon for different applications. Before going to that, I showed you some examples of coconut uh, coir, but this can be extended to other biomass also. when you look at it, we work on sugar. This is different. Sugarcane bagasse, teak wood, rice husk, bamboo, and banana fiber. If you look at it, the morphology is completely different. And similarly, the microstructure also is different, and the graphitic content is also different. So here, you also have the possibility to change your uh, biomass, and that can yield another kind of carbon with different morphology, different porosity, different functional groups, as well as different um, graphitic content. So this also you also need to keep this in mind that different biomass we have, uh, the final carbon will be different in the case of different biomass. Now, examples. So now we move on to properties. Okay. So this is one thing that we could look into is this pyrolyzed carbon, which is from the coconut coir, is inherently piezo-resistive. Changes its resistance with force. And since these are mechanically stable, we could look into the piezo-resistive property of a single fiber. So this is that example. And one thing, just keep this in mind, is about the trend that we observe. What we observed is that as the temperature is increasing, as the pyrolysis temperature is increasing, the piezo-resistive sensitivity is coming down. That means the sample pyrolyzed at 600 degrees Celsius is more piezo-resistive than the sample pyrolyzed at 1000 degrees Celsius. Even though the graphitic content is increasing, when you increase the graphitic content is increasing, the conductivity is increasing. So you can see this is the conductivity here. The conductivity is increasing. And from Raman, we could see that the graphitic content is sp2 content is increasing, but the piezo-resistive response is coming down. Now you can actually make this not as single fiber. You can powder it and make sensors out of it. So this, what you see here in the figure, is a small sensor which is formed by this powder. You powder it with a ball mill. And this is a very simple design. Like you have a substrate, PET substrate or something, flexible substrate. Then you put a double-sided tape on that. Then you spread this TCP 600, we call it, like it's a sample that is pyrolyzed to 600 degrees Celsius. And then you put connect it with two copper wires. And on the top, you put adhesive to kind of protect this powders. We use Fevicol. Okay, so maybe we can think of something like a 10 rupee sensor. And this sensor works. And the trend is same actually. As you increase if you use different powders, which is pyrolyzed at different temperature, you have a decrease in the piezoresistive response. This actually can be used as, so this is first actually is a prototype, which actually is working for the last maybe 1.5 years or so. So this means that these sensors are durable, and also you can use it for uh, motion sensing and okay, and it can also sense air flow, and also basically you can use this as touch sensors, movement sensors, and other things, and then it is actually durable. You can see uh, it is, I think, more than 10,000 cycles sustained without any changes. So here you can use this powder to make sensors, and you can tune the sensitivity. That is the point. As you can see, you can tune the gauge factor, which is the sensitivity. So you can tune it by changing the pyrolysis temperature. So you might not always want a very high sensitive sensor. So actually, by changing the pyrolysis temperature, you have a change in the piezo-resistive response, and then you can basically uh, have a sensor with the tuned sensitivity. Now this is one thing. Now another thing is shielding, EMI shielding. So electromagnetic interference is a big problem. So people are coming up with different materials to have the electromagnetic shielding. And metals have been used, but the problem with metals is it is heavy and other things. Another possibility, people started using uh, biomass derived carbon. There are some works on straw derived carbon and all. And actually, we use the coconut shell to see whether we can actually have some, whether it has some inherent electromagnetic shielding. We make small pellets out of it with um, some binder. And this is actually the sample which is dispersed with nickel. So here we increase the graphitic content. We had the non-catalytic samples also, but also we improved the graphitic content by adding both iron nitrate and nickel nitrate. Here the thing is that you are increasing the graphitic content as well as you are dispersing some nanoparticles, because these kind of metal nanoparticles will help in enhancing the EMI shielding, and we do all these things with single step synthesis. And these are some of the micrographs, TM micrographs. What you can see is that there are nickel particles, and as I told, there is this graphitic region which is covering the nickel. Now here, even though the nickel and iron is not exposed, uh, it can enhance the EMI shielding properties. Now, in the graph here, the first three is that is heated to 1000 degrees Celsius without any catalyst, and it is the shielding efficiency is being measured in an X band. So usually something what anything above 20 dB is considered as a decent shielding material. So you can see the CSP 1000, this is shell 1000, is actually showing somewhere around 25 dB without anything. You just heat it. And here the trend is reverse. Here the trend is that if you increase the uh, graphitization temperature from 600 to 1000, you have an improvement in the EMI shielding, because now it is becoming more conducting, because here you need to have more conducting and the porosity is increasing. So you will have the local internal reflections and all, which improve the EMI shielding. And if you increase it further with catalyst, you increase the EMI shielding. And I think this nickel sample is showing somewhere around more than 50 dB, the nickel dispersed sample. So here the trend is different. Previously, we saw that when you increase the temperature, you have a increase. When you increase the pyrolysis temperature, you have a decrease in the property in the piezoresistive response. Here, when you increase the temperature, you have a increase in the EMI shielding properties. Now, one more thing that is a slightly different response, which is a relatively new field, which is called hydrovoltaics. Hydrovoltaics is basically when water is in contact with, in this case, carbon. Okay, when a flowing water is in contact with carbon, there can be some electrical double layer formation which separates out. The water basically interacts with the ions on the surface of the carbon, and there will be an ionic movements of ions in the direction of the water flow, and there will be a movement of the electrons through the carbon. And basically, you can produce some power by just flowing water across the carbon. Here, three things are important, I would say. One is the surface area of the carbon. More the surface area, more the interaction, and more the possibility of forming double layer. Second thing is the conductivity of the carbon, because the carbon has to conduct the electrons through the carbon. So it has to be more conducting. Third thing is the availability of surface functional groups to interact with the water. So again, we tried this sorry with so tried this with uh, coconut coir, because we know that this is highly porous, okay, and has a moderate conductivity, not though so high. The conductivity is decent because we have tested it previously. So we made a sample, which is, I think, this next one. Yeah. So the sample is very simple. So you take a tube, you fill it with carbon powder. Okay. You put a cotton wick below, because the whole thing works like, the water will evaporate through the carbon powder in the tube. So the tube is filled with carbon, and you put it in water, so that the water will evaporate through the carbon, and there will be a flow across it, and that flow will produce some some voltage and current. So this is one video, which a small sample is giving almost 1 volt and some 0.2 milliamps of current, or 200 microamps of current. With that just small sample, without anything, it is just evaporating. And we just looked at again different possibilities and things. And when you have again, okay, so this is what I want to show you. So the first case, we saw that as the pyrolysis temperature increases, the piezoresistive response is coming down. And in the case of EMI shielding, we saw that when the temperature is increasing or the graphite content is increasing, we have an improvement in the EMI shielding. Now, in this case, we have samples from 600 to 1500. So we increase the pyrolysis temperature, and we went beyond 1000. We went to some other institute where the facility is there, and we heated to 1200 and 1500. So basically, now the sample is not, it is more graphitic, right? There is no nickel and all, but it is more graphitic because you have increased the temperature and you're going up. Now, what we observe is that the maximum performance, if you look at the voltage and current, is not happening for the sample which is at 600 or at 1500, because it is happening somewhere in between, which is the sample which is heated to 1000 degrees Celsius. Now, here is the thing that I want to show, because now the trend is something different. Initially, it was reducing with increasing graphitic content, the piezoresistivity, but the EMI shielding was increasing with increasing graphitic content. But in this case, the best performance is happening somewhere in the middle. Now, this is mainly because of two things, I would say, because as we increase the graphitic content, the conductivity will definitely increase. But when you increase the graphitic content, the porosity, after some time, the porosity will come down because of the formation of this highly graphitic layers. The porous nature of the carbon comes down drastically, that you can see from the BET. And the second thing is that as it becomes more graphitic, the functional groups in the carbon comes down. So here in this case, you have a perfect microstructure, morphology, as well as the chemistry in the carbon to have higher uh, performance, higher voltage and current. So here the trend is something different. So you can tune your material. Actually, we could again do this, improve this by functionalizing the carbon. I haven't shown this. So you functionalize the carbon again, and then the output has improved drastically. But you can actually see a demonstration of this. This is from for small samples, you can actually light an LED, uh, and yeah, so and this this has translated into kind of a product uh, that you can actually. This is a modular design that we designed, and each of them is a single device, and you can connect it in series or parallel, whatever it is, and in fact we could light three LEDs for maybe, I think, 3 hours, and even more than 3 hours. So this is one way that makes us happy, that kind of translated from a simple um, elemental investigation on the microstructure and effect of microstructure, morphology, and chemistry on the generation, and then we could use that uh, information to further translate into a working prototype. Now, all these things I'll just take maybe 5-10 minutes. So this is all what we have seen. This is how you engineer the uh, carbon with pyrolysis, right? So whatever we have seen is conventional pyrolysis, which is you just keep it inside and then give some inert atmosphere and heat, which is power intensive, and so even though the source, we can say, it is uh, biomass and sustainable, we could say, but the process is not sustainable. Uh, so then actually people have started thinking of some non-conventional process to make these kind of carbons. Uh, one thing is that the laser induced graphitization. You can use laser to graphitize polymers as well as biomass uh, to highly graphitic carbon within very short time, because it is fast. Uh, and also there is something called a flash joule heating now, because you give very high power and high voltage for a very short time, and then you can convert uh, these things into highly graphitic carbon. People have also used microwave pyrolysis to microwave, because carbon is uh, microwave active, so you can actually heat carbon with microwave. Some examples, then I think we'll stop. We actually with these kind of laser module. This is a normal laser engraver that you can buy these days from Amazon and all. You will have a laser, and actually you can graphitize some polymers. Now, one example is the polyimide. So you can take this polyimide, which is also called Captain tape, to. So these are examples of the graphitic carbon which you got with, sorry, laser graphitization. And to tell you that one main difference with the conventional pyrolysis is that these carbons are highly graphic because of the photothermal interactions with the laser. This becomes highly graphitic in a very short time. You can also do the similar thing with coconut or biomass also. There are works. And one good thing with the laser is that you can actually selectively graphitize because of the movement. Because this laser, always these things come with a movable or a stage with precision, right? So I think you might have seen this is the same thing that people use to make photos and all, laser engravers, laser engraved photos and all. But you can put a design, and basically you can carbonize or graphitize, I would say, in a specific pattern that you want. And this is one of the things that we do here recently, is to make all carbon microheaters. So you can graphitize in a specific pattern, and you can use that, because once the carbon is made, then that is conducting, and you can actually do a resistive heating. And the carbon, as I told, is very stable in inert atmosphere at very high temperature. So you can you can reach very high temperature. So I think we have crossed even that. Now I think these kind of small heaters reach around 1200 degrees Celsius in inert atmosphere and almost like 650 degrees Celsius in open atmosphere. So and the what is interesting here is that if you think of a micro heater with usually it is made with metals, okay, and the process is really labor intensive and costly. You need a mask, you need different deposition systems, and changing the design or changing the size, you need to change the whole process. But here, you can make it in any size, any shape you want, because you need to just change your design and put it into the laser engraver. So you don't have to worry about changing the design. So this is basically, if you see here, this is a meander design, and this is first design. Then we moved into this. Then finally we have moved into something like this, and this is which yield and the design again. The design as well as the laser parameters define your maximum temperature and how much area you want to heat. So these things can be precisely controlled. So this is okay. This is a video which shows that it is reaching around 1300 degrees Celsius with the thermal camera, and I think I have a video. So this is a LED strip which is on the top of the heater, and we can see that the heating is very fast, and then it is melting. So you have the possibility. I just showed this to let you know about two things. One is that you have non-conventional processes which can be used to make highly graphitic carbon, and one of this is laser-induced graphitization, which can actually precisely pattern polymers, or you can make carbon patterns. That is an interesting thing, and it is fast and precise, so that you can make heat and other. And and also these carbons can be used uh, not only for heaters, but you can actually change the surface properties with changing um, the laser parameters. So you can see this is a super hydrophobic surface which is formed by laser graphitization, and then you can tune the contact angle with with by changing the laser parameters. Some examples, is not only limited to just graphitization, but also you can use it optimize different properties. I'll just I think I just want to introduce this synthesis also, which is called a flash synthesis of graphene. And what they do, I have a video from Rice University. So what they do is, are you are able to see the hear the audio?
No, sir.
Okay, then leave it. Look, so what they do is that they actually take uh, conducting initially pyrolyzed carbon from any biomass or anything, or mix it with some conducting fillers, and they give very high voltage and very high current for a very short time. So, like in the case of laser, you have a very fast conversion of uh, this organic things to highly graphitic. So I think there is a small video where you can see. So this is the carbon inside. So you can't flash biomass as such, because there should be some kind of conductivity associated with it. So either you mix it with some conductive carbon, or you initially carbonize it to some extent and then do this, and then you can give very high current and voltage. And you can see that. So this is why it is called flash synthesis. Uh, so you can, the good thing is that this carbon is actually highly graphitic. Um, and it's ultra fast, energy efficient production, and it is very low cost. And you can use basically any kind of waste derived feedstocks. It is scalable. You can have gram scale synthesis of moderately good graphene, I would say, because making graphene in gram scale is a really challenging thing. And this there are videos where they automate it to make it continuous and all. And the high quality turbostatic graphene, this is the thing. So you can use it for uh, uh, you can apply it for across advanced technologies. So the last two or the I just want to convey to you that it is not only the normal pyrolysis which is being carried out. People are coming up with new ways to convert um, these waste and biomass into. They have done. I think they have flashed a lot of things. Lot of things about all biomass, human air, all those things. So I think they have tried and they have assessed the quality of the graphene. But basically, uh, you have processes where you can actually use these kind of non-conventional pyrolysis to come up with highly graphitic. Again, these are all tunable. You can tune the properties with the process parameters. You can tune the microstructure with process parameters, and then because of that, you can tune the properties with the process parameters. So yeah, I think I'll stop here. Uh, Pyrolysis offers green circular approach, and pyrolyzed carbon exhibit tunable properties. It can be used in a variety of different applications. But the problem with this is that the process optimization. So we now started looking into a lot of people started looking into how to make the process more efficient. As I told, if you heat your sample in a furnace for 10 hours uh, and then make some carbon, and that doesn't make much sense because the whole process is not energy efficient, and the carbon footprint that you are leaving is far more than that you can save by making a carbon and using that carbon in different applications. And you have to again start tuning it. Understanding the process more will help you to tune the properties more for multi-functional, super performing materials like this turbostatic carbon made from flash and all is as good as the properties are very close to graphene, I would say. And we should start seriously thinking about the life cycle assessment and quantifying the environmental and economic benefits of this kind of carbon. That will help you to have some sustainable way to mass produce these things, and hopefully we could see more of these kind of sustainable carbon in future days. Just before we stop, so we are from we call ourselves laboratory of applied microscopy and spectroscopy. We do some we do basically research in carbon and as well as some method development. We are always open for any kind of collaborations or any kind of you can visit our lab. You're always welcome, and you can encourage your students to have internship and all. NIT has an official internship being called every year during this time, and it is through the CCD. And otherwise, also we used to host a lot of very good internship students. You're also welcome. And if you don't know, the material science department has an MTech in material science and engineering. It has both um, gate entry as well as the non-gate entry. So if some of your final year students or someone is interested, I think the first phase is over now, but definitely there will be some spot admission, and yeah, ask them to just watch. And yeah, I couldn't stop without thanking all these people because I usually don't do any experiments these days. I take their results and present it to you. So all these things are uh, whatever I've discussed is from these people and the collaborators and the funding agencies which help uh, with the facilities and funding. Thank you, and thank you all for the patient hearing, and I'll be happy to have further discussions.
Thank you, sir, for the session. I'm sure it was very interesting and fruitful for the participants. Now, participants, if you have any queries, you can ask. The platform is open now. Hello, Shyam sir.
Yes, yes, please.
So almost most of the techniques mentioned today was to develop graphene, no? SP2 based graphene, right?
Yeah.
So whether
Uh,
we can make use them to convert to CNT, carbon nanotubes, whether there will be any
um,
difference in the strength in them.
yeah, okay. One thing is that we are not exactly making graphene. We are making, I would say, graphitic carbon. Okay, so everything will be sp2, but it might not be layered, and then you will get um, you are not making single layered graphene and all. But this biomass pyrolysis normally won't yield carbon nanotubes because carbon nanotubes need to be processed in a very special way. Then only you will have that directional growth. So usually you won't get, or it is very unlikely to get carbon nanotubes by the pyrolysis of or normal pyrolysis. You might need to have some special kind of directional mm, growth and all. So CNT will be difficult.
Okay, thank you. So any more questions from the participants? I don't think there are any more questions
Okay.
from the participants. So on behalf of Sripati, I would like to thank Dr. Shyam Kumar for delivering the session. It was a wonderful session for me at least. I, mm, I think we can wind up the session. I'll share the
Okay.
feedback form now. You can fill the feedback form and we will meet again tomorrow for the next session. Okay, so tomorrow morning you have the second session from Dr. Nilesh Ashok. So participants, please be ready with your laptop for that hands-on session. Thank you.
Okay. Thank you. Thank you all again. And thank you, Manoj, for the invitation. Thank you. See you then.
Sure. Thank you, sir.